Alright, so this is the first video on my channel, and so as you can see from the title, probably what we're going to do is try to solve some work slash rate problems, right? So these are usually not that difficult if you have the basic work rate formula down. Let me write that down right here. So as we all know, wait, okay, sorry, that happens, I forget to change the color. Work, any sort of work, equals the rate into the time. Alright, and I'll just define these terms before working on the rest. This for the rest of this lecture is going to denote any sort of amount of something that we do. Okay, amount of something done, or what we're gonna do. Okay, it could be anything. It could be building walls, which a lot of problems that I'm going to do is about building walls. It could be typing. It could be your work in physics too. It could be any sort of amount of something. Okay, that's being done. All right. So that's what the work. The rate is the speed. Okay, the speed at which we do the work. Okay, now speed does have more technical definition in physics, but here we just mean the rate. Okay, the rate at which we do the work. Okay, speed of doing, how fast are we doing our work. Okay, and time, I guess that doesn't really need to be defined. How long we take to do the work, basically. Well, I'll just write that down for sake of completion and mental satisfaction. Duration. Okay, so, or how long it takes to do the work. All right. So as I was saying before, if you have this formula pat down and have been using it for a long time, you probably wouldn't encounter any difficulties in quite a few problems. But then if suppose say the three variables are all different, okay, problem, then you might be a bit confused. It could still be solved if you consider some variables for both cases, and then use this work rate equation. But then the situation gets a bit hairy, it becomes a bit confusing, and that's why we are going to simplify these sorts of problems. Okay, we're going to derive a formula with which we can solve these much easily, okay, much more easily. All right, so to do that, let me take this formula. So we have work equals rate into time, right? So if we divide both sides by the product of rate and time, what we get is work divided by rate into time equals 1. Okay, or if you're very conscious about units, in general, if the units are different for these quantities don't really have matching units, then it would equal some constant. But anyways, it's let's just consider it to be 1. Okay, it could be some constant, but that would as you'll see later, it wouldn't really matter, because okay, so W divided by the rate into time equals 1. All right. So this is, now if we have one situation where this holds true, okay, suppose say for one instance our work is W1, our rate is R1, okay, our time is T1, and we know that's going to equal 1, right? We know that's going to equal 1, okay. And same thing again, if we have another instance of doing the same activity, then W2 divided by R2 into T2, T sub 2 equals 1 again, right? Alright, so this is 1, this is 1. So shouldn't these two be the same as each other? This expression and this expression should be equal, right? Alright, so we can thus say that W1 divided by R1 T1 equals W2 divided by R2 T2. Okay. And I'll just keep an eye on my battery. It goes out pretty quick. Oh, I might have to plug the charger. I'll be back in a sec. Right, sorry for the interruption. So as I was saying, Yahoo, we have already derived our formula. So I'll box this in. This is our formula, provided that we use the same units for the quantities on both sides or both expressions. What I mean by that is, suppose say this is in suppose say let's see, the number of kilograms we lift, suppose say kilograms we lift, okay. This has to also be in kilograms, it cannot be in grams, all right. So this also has to be in kilograms. If the rate were, and I'm not going to be consistent with a lot of physics theorems, so but anyways, just for example's sake, suppose say this is in newtons, okay. So this also has to be newtons, not kilonewtons or anything, okay. So kilo, no, that's not allowed. So this also has to be in newtons. And if this is in days, I think you get the idea. This also has to be in days. So provided that the quantities on the two sides are the same, this is going to hold, okay. As I was saying, if you're a bit conscious about units, this formula you can justify it by saying that, okay, so this is going to equal some constant and this is going to equal the same constant if we keep the units the same, okay, on both sides, and that's how we get this formula, okay. So it's always going to hold true provided that we use the same units for the quantities on both sides. All right, so with the formula derived, let's try to solve some problems with it, okay. All right, so I have this problem on hand. Worker A can build a wall in 5 days if he piles up the bricks at a rate of 12 bricks per hour, right? So I'll highlight this now, A wall, so that's one wall, yeah, that's one wall. Worker B having the same working hours as A, okay, as worker A, so we don't have to worry about some difference in shift or anything. Can build the same wall in 6 days, okay. Actually, I'll highlight all the numbers, that's a good idea. So 5 days and 12, and I'll do this in yellow also. So that's for worker A. For worker B, can build the same wall, okay. So same one wall, okay, the same one wall in 6 days, all right. All right, so the question is, how many bricks is worker B able to pile up every hour, okay. So basically there asking for the rate. Okay, how many bricks every hour, so they're asking for the rate. All right, so as we can see here, all right, so first let me solve this using our formula. Okay, so you have, as you can see, W1 divided by the product of R1 and T1 equals W2 divided by R2 and T2. So let's set this up. So we have W1 first, so that's going to be, we can just put 1 here, okay, because as I said, the units just have to be the same on both sides, but doesn't matter what sort of units we use. There's no SI unit restriction or anything like that. Okay, so even 1 wall, okay, the unit wall is completely valid. Okay, so we have 1 wall. The work done is 1 wall. Okay, worker A is building 1 wall, so this is for worker A. All right, and he builds it. I'll use the same red color. Need to be a bit more consistent with the colors. Anyways, so, and he builds it at a rate of 12 bricks per hour. Again, I'm using bricks per hour, not bricks per days or anything, but that doesn't really matter because the units, again, as I said, they have to be the same on both sides but not consistent per se. Anyways, there's some and there's thing about the shifts and everything, so we should not actually use days here. Anyways, 12 bricks per hour. Okay, and he does this in 5 days, right? Yeah, 5 days, so T1 is 5. Now this is going to equal the same expression for worker B, right? So for worker B, we have the same 1 wall. Okay, 1 wall, and well, we need to find the rate. Okay, we need to find the rate, so I'll put R2 here. Okay, and this is multiplied by so he does this in 6 days, right? Yeah, worker B does this in 6 days. Okay, and voila, we have our equation all set up. Now we just need to solve this, and the easiest way to do this, I think, would be inverting both sides, taking the reciprocal of both sides. So if we do that, it's 12 into 5 divided by 1, that's 60 on this side, 60. That will equal 6 into R2 divided by 1, which is just 6 into R2. Okay, and that gives us R2 equals 10. Now we need to be a bit careful at the end. We want to put this number into context. Just the number 10 doesn't really make any sense. So as I said, if we use this formula, the units on of the quantities on both sides are going to be the same. So the first rate was what? It was in bricks per hour, right? So this one is going to be the same. Okay, it's going to have the same units. So worker 2 has a working rate of worker B has a working rate of 10 bricks per hour. 10 bricks per hour. All right, so that's this problem solved. Now, if you might have noticed, and if it's good that if you have that we have the same work for the same amount of work for worker A and worker B. As well, this problem could have been solved more simply if we just took the product of rate and time. That's going to be one work in the work for worker A. That's the same for worker B. So basically, the product of rate and time, we take it for both the workers and just equate them. So that would have been the simpler thing to do in this case, because the work is the same. And in general, if one of the variables is constant for both cases, then the situation becomes much simpler. You can rearrange the work rate formula and do it much more quickly. However, what I'm trying to do is this formula is for the purpose of it's to reduce our confusion. All right, as you'll see in the next problem, it's not this formula really shines through. Okay, so let's just move to the next one. And this was the situation I was talking about before, where the variables, all the variables are set different. Okay, all the variables are set different. Okay, so worker A, now this is a different problem. Just slightly modified from before. Worker A can build two identical walls. So worker A now builds two walls, okay, in 10 days. So for the two walls, he takes 10 days. All right. If he piles up the bricks at a rate of 12 bricks per hour, okay, so 12 bricks per hour, that's his rate. Worker B can build the same type of wall at a rate of 15 bricks per hour. Okay, so that's his. Okay, not that cool. So 15 bricks per hour. Okay, that's worker B's rate. If worker B does his job for 36, actually I just had an idea. I don't know why I didn't have it before. I could just write what these quantities are here. This is R2, write that down. This is T2. Okay. If worker B does his job for 36 days, okay, how many walls would he end up making? Okay, so what we are asked for is wait, I'll go back to that. So how many walls? So what we are asked for is W2. Okay, now write the labels for the previous ones too. So this one is W1. Okay, this is T1. Okay, and this is, just to make it a bit clearer, okay, and this is R1. This is R1. Okay, as you can see, all the variables are now different from each other. W1 is probably not going to be the same as W2, even if it is, since we need to solve for this, there's no point in thinking about that. R1 and R2 are different, and T1 and T2 are also different. Okay, so now if you were to try to solve this formula using some rearrangement of the work rate, solve this problem using some rearrangement of the work rate formula, you would have to consider a few variables, and it would take some time. Okay, it would take a considerable amount of time. Okay, but using the formula that we derived, it's actually much more simpler. Okay, so all we need to do is plug the values in. So we have W1 divided by R1 T1. Okay, so 2 divided by R1 12 into T1 10. Okay, this is going to be the same as W2, which is, we don't know, so that's that. Divided by R1, sorry, not R1, R2 into T2. Okay, to T2, which is 36. All right, and we can rearrange this to get, let's see, W2 is same as 2 into 15 into 36, 12 into 10. Okay, so we can do some cancellation here. So this goes out, this is 3. Okay, this goes out, this is 5. This goes out with this is 3. So all we have left is 3 into 3. Okay, so that's 9. It's 9. So and the unit for our work has to be the same on both sides. So this was what, 2 walls, right? This was 2 walls. So W2 is actually 9 walls. Okay, so worker B ends up making 9 walls in total. Okay, so as you can see, this was pretty easy using our formula, and would have taken quite a bit more time if we just use some rearrangement of the work rate formula. All right, so let's do another problem. Okay, so here, let's see. Beth, a journalist, can type 80 words per minute, okay, WPM, for her article. Okay, her colleague Jean, who has a typing speed of 60 WPM, has to finish. Okay, wait, it's not doing what I should have done. So this is R1. This is the rate. Okay. Okay. Let's see. For her article, all right. Her colleague Jean, who has a typing speed of 60 WPM, so that's R2. Okay, has to finish an article 25% longer than Beth. Okay, so this information, we'll interpret that in a bit. So this is basically talking about how much work Jean has more than Beth. Okay, so that's going to be really useful, a very crucial piece of info. I'll keep that aside for now. Okay, in half a month. Okay, so this is T2, right? Yeah, this is T2. This is T2. Okay. Assuming that both journalists complete their work right at their respective deadlines. Okay, not something that we should do. Procrastination leads to consequences. Okay. How many days does Beth have to complete her article? Okay, so how many days does Beth have to complete her article? Okay, now, well, what we are being asked for is what? T1, yeah. How many days Beth? So it's T1. Okay, so let's set up our equation. So we have W. Okay, W1. This is basically Beth's work. Okay, how much work Beth does. We'll discuss about that in a bit. I'll just set up the whole equation for now. Then I'll make a simplification, substitution, you could say. Divided by R1, which is 80, into what we need to find, which is T1, equals wait, sorry, different color. So that's W2 divided by R2, which is 60, multiplied by T2, which is half a month, and the answer that we want is in days. Okay, we could do the conversion later, but it's not really I think it would be more convenient to do it now. So half a month is 15 days. Okay, if we do this, if we use days here, we're going to get the answer in days here, this here too. That's going to be very convenient. And this is what I was talking about before. Now suppose, say, Beth's article, you could say that this Beth's article is X words long. Okay, suppose say it's X words long. Okay. So W1, you could also say that this is X. Okay, this is X words. And it said that Jean's article is 25% longer. Okay, so basically if we do it for Jean's, we have 1. Okay, so 1x plus what? So 25% or 0.25%, 0.25 0.25 into x. So, and it's 25% longer, so that's why the plus. Okay, that's why the plus. And we get that Jean's article will have 1.25x words. Okay, Jean's article will have 1.25x words. Okay, if you're really good at this sort of mental arithmetic, you could really quickly just write 5 by 4 x here, okay, and a lot of people wouldn't really even need to write the x, okay, make that sort of substitution. So anyways, um, we'll just do that. We'll just substitute it here. So w2 is 1.25 x, okay. So now this equation might look like we have two variables, but one of them just cancels out right here, and all that we have is the variable that we want, t1. We can solve for this. Let's see. And again, I think the most convenient thing would be to invert both sides. So AD into T1 divided by 1, so it's just 80 into T1 equals 60 into 15 divided by 1.25. 60 into 15 divided by 1.25. Okay. Now, well, I could do this by hand. But let's just use a calculator. Okay. And by the way, I'm using the Casio emulator. This is pretty handy. You might want to download it. So here, let's see. 60 into 15 divided by 1.25, and we can basically to find t1 we can bring 80 to this side, so divide by 80 on both sides. So 1.25 into 80, okay, this should give us our answer, and we get 9. Okay, we get 9. So t1 equals 9, and this should be in days because we used days on this side. Okay, so t1 is 9 days. So Beth has 9 days to write her article. All right, so that problem is also done. It was pretty neat, right? Pretty neat, pretty easy. Okay, so this formula is proving really useful. Now there's another type of problem where this formula also shines through. I just need to make a bit of modification. This is called this topic is popularly called combined work. Okay, let's just read an example. So worker A can build a wall in 5 days if he piles up the bricks at a rate of 12 bricks per hour. Worker B can build the same wall in 3 days. Okay, in 3 days if he works at a rate of 20 bricks per hour. If the workers together build a single wall, okay, how long would it take? Okay, as you can see, both the workers are joining in and building a single wall. So this is their efforts are being combined. Okay, their rates are being combined, you could say. So that's why these problems are commonly branded by the label combined work, and these prove a bit more tricky sometimes. Okay, you'd need to work through quite some steps. If you just use the regular rate, work rate formula, and use take some variables and substitute, etc., it would take some lines, some time. You'd still get the answer, but our formula, the one that we derived, can do this much quicker. Okay, but we would need to make a bit of a modification. For that, let's just see what happens. First thing, what we can see is, okay, so for our example, there were 2 workers. So for the first worker, this is true, w1 divided by r1 t1 equals 1. Same thing for the second worker, same expression, equals 1. All right, so what I'll attempt to do is I've been using red a lot. Let's use orange. That's better. On one side, I'll keep the 2 expressions added together, w2 okay, and on the other side, well, attempt to do is keep the combined the expression for the combined scenario, okay, like when both of them work together. Suppose say the work is W, okay, the work is W, rate is R, and the time taken is T, okay. And let me just be clear about something. You just need the work W1 to be done in at the rate of R1 is during time T1 for the first worker. This just has to be true. This just has to be true. But it's not really necessary that suppose say W1 and W2 their sum equals W. So it's not necessary that these works are such that the combined total is the whole work, okay. So we could just be given some info about basically how the individuals work, how their work progresses, but the combined scenario can have some different. Anyways, we'll see problems like that in a bit, but anyways, this is what I'm attempting to do, but I don't think the equation is correct yet, okay. It's not correct yet. Let's see what we are basically doing. So as I said, this expression we just derived, this is 1, right? Okay, this is also 1, okay, and this also has to be 1, okay. It is some work divided by some rate into some time, for same same scenario, the same activity. So this also has to be 1, provided we have the same units for all the quantities on all sides, for both sides, okay. So this also has to be 1, and if that's true, we cannot really just equate them, right? We cannot just equate them. So we'll have 1 plus 1 equals 1. That wouldn't be true. But what if we multiply by 2? What if we multiply this side by 2? Okay, then these two would in fact be equal, right? Then these two would in fact be equal, and this is my formula, okay. This is my formula. If you're wondering what how would it look like in the general case, suppose say there are n number of working elements. They could be people, machines, anything really. So we have W1 divided by R1 T1 plus W2 divided by R2 T2 all the way up to the very last person or element, whatever it is, divided by Rn Tn. This is going to equal I'll do that in a different color. W, for the combined scenario, I'll just say it's W, the work, divided by R into T multiplied by, this is not going to be 2, this is going to be, now let's just think about it. We have 1, 2, 3, 4, so all the way up to n. So this we're adding n ones, right? We're adding n ones plus 1 here plus all the way up to this, and there are n of these, right? There are n ones here, so there are n ones, okay. That's why this sum is basically n, right? So we just need to multiply this by n, okay. We just need to multiply this by n. This is just a generalization of what we did here, okay, where n is 2, we could say. So basically this is our formula, okay. This is our formula for combined work, okay. This expression, again, it's basically this expression, okay. This expression is you could say a cornerstone for this lecture, this topic, okay. This expression for all the individuals added together, will be equal to the same expression for the combined scenario, multiplied by n, okay, multiplied by n, which is the number of individuals or working units. All right, so since we have this formula, let's try to apply it. Let's try to apply it here. Okay, now this should be easy. I'll start adding notes here. So 5 days, right? So this is T1. If he piles up the bricks at a rate of 12 bricks per hour, so this is R1. This is R1. Worker B, okay, A1, and this is W1, right? So 1, this is 1, and this is W1 basically. This is basically W1. Okay. Worker B can build the same wall in 3 days. Alright, so same wall in 3 days. So this is T2. If he works at a rate of 20 bricks per hour, okay, so this is R2. Okay, and same wall, basically it's one wall, right? Okay, so it's one wall for worker B2. So that's W2, which is basically 1. Okay, so if the workers together build a single wall, now this is them working together, so we know that this is our combined work problem. Again, this is our W. This is the work for the when their efforts are combined. This is W1, that's going to be 1. Okay, 1. This is basically 1. How long would it take? Right? How long would it take? So what we need to find is T. Okay, the time for building the wall when their efforts are combined. Okay, so let's just set up our equation first. So we have W divided by R into 2, so C, so T. So for each of the working units, here it's just two of them. So we have W1 1 divided by R1 12 into T1, which is 5, plus W2, which is again 1, divided by R2, which is 20, multiplied by T2, which is 3. This is going to equal, now we have W, which is again one wall, divided by R. Now the rate, since these two workers for the same well, I forgot to write it, I guess, but their shift timings are the same and all, the same duration, and also the rate, their combined rate, and should be pretty obvious, is just their rates added together. Okay, so in 1 hour, worker A does 12 bricks, piles up 12 bricks. Worker B piles up 20 bricks. So as a whole, when their efforts are combined, the rate is 32 bricks per hour. So this is 32. I'll just pause for a bit. Alright, so I'm back. Where were we? Okay, so one wall divided by 32, that's our rate for when their efforts are combined, multiplied by switch to yellow, multiplied by the time taken, right? How long would it take? So that's what we need to find. So T, oops, yeah. Okay, so that's T. Okay, and we're not done. So here we have 2 workers, so we need to multiply by 2 on this side. Need to multiply by 2 on this side. All right, so that should be our equation. Now we just need to solve it. Okay. So this is 1 over 60, this is 1 over 60, and both, if you add them, you get 1 over 30. This is equal to 2 by 32 is 1 by 16. 1 by 16t, right? If we take the reciprocal of both sides and then divide by 16, we get t equals 30 divided by 16, and that's what, let's see, it's 15 divided by 8, yeah, 15 divided by 8, which is 1.875, yeah, 1.875, 1.875, and this should be in what, this t was always in days here and here, so this is going to be in days too. So the two workers together need 1.87, wait, is that, no, wait, was there was there something wrong here? This shouldn't be the answer. Yeah, this, oh no, yeah, that it is. I was confusing this with, okay, this problem, yeah, this problem. I'm really sorry about that. Okay, so yeah, this is definitely the answer here. So yeah, it is 30 by 16, which is 1.875. Yeah, that's the correct answer here. Sorry about that. All right, so that's done. Okay, that's done. It didn't take long at all. Okay, just a few steps, and you got your answer. Okay, that was fairly easy. Let's look at a slightly modified version of the problem, and I encourage you to pause the video and try it yourself. And all right, I'll assume that you did. Now, if I a couple of years back saw this problem and wasn't thinking about much, really, approaching this in some sort of bird brain method, what I'd this would be my thought process. So okay, there's like, let's even draw this thing. Okay, so we need to build two walls, right? Okay, let me read the question first. Worker A can build a wall in 5 days if he piles up the bricks at a rate of 12 bricks per hour. B can build the same wall in 3 days if he works at a rate of 20 bricks per hour. If the workers together build two such walls, okay, two such walls, how long would it take? So this is what my bird brain from a few years back would simulate the situation as. Okay, so we have both the workers. So okay, long legs, long legs. So this is A, that's B. Okay, so let's start building. Okay, so if they start building at the same time, and suppose say 3 days pass. Okay, 3 days pass. They're working together to build the walls. Okay, so in 3 days, worker, if suppose say they are working on the wall separately, worker B should have made a complete wall, right? It's as it's said in the question, worker B can build the same wall in 3 days. All right, and suppose worker A has built a portion of the wall. Okay, portion of the wall, and now what my bird brain would think from few years back is, okay, so worker A can continue his work for a while longer. Okay, so he needs 5 days in total to finish this, right? Finish his wall. So another 2 days, suppose another 2 days, and that should give me an answer, a very dubious answer actually. Wait, not days. Okay, a dubious answer of 5 days. 5 days. Okay, and I'll leave a question mark here. Okay, so is this correct? Well, no. And where did my logic fail? It sounds nice, but the thing is, to build this portion of the wall, it's not like worker B is just going to sit around and not do any more work. Okay, that's not being said in the question. So after worker B is done with his wall and worker A is done with portion of his wall, they're going to work on this together. Okay, they're going to work on this together. So it's not going to take 2 days. This portion is not going to take 2 days. So that logic cannot be applied. Okay, that logic cannot be applied. So it's not going to be 5 days. Should be a bit less than 5 days. Okay, that's why this would be wrong. The correct thing to do would be to just resort to our formula and mathematical logic. Okay, so safe and sound logic would be, alright, so this is our T1. Okay, this is our T1. This is our R1. This is our R1. Alright, this is our okay, this is A wall 1. Okay, so this is one wall. That would be W1. Okay, now for worker B, same. Okay, so that's one wall, and that's going to be W2. Okay, and takes 3 days, so that's T2. It's T2. Okay, okay, if he works at a rate of 20 bricks per hour, so that's R2. It's R2. Okay, if the workers together build 2 such walls, so that's the when their efforts are combined, the combined work part of the problem. So this is W, which is 2. Okay, this is 2, which is W. How long would it take? So this is T, which I need to find. Pretty similar to the previous problem. In fact, it's really almost the same if I haven't changed the number. Okay, I did change the numbers quite a lot. Okay, so it's pretty much the same as before. So we have W divided by R into T for the first worker added with the second worker. That would equal the combined the expression for the combined situation multiplied by the number of workers, right, which is 2. Let's do that. So we have W1, which is 1, divided by R1, which is 12, and T1, which is 5, plus W2, which is again 1, divided by R2, which is 20, multiplied by T2, which is 3 days, and this is going to equal now we're building 2 walls, right? Yeah, we're building 2 walls now. So 2 walls divided by our rate. Again, it's going to be 12 plus 20, that's 32, same as before. Yeah, 12 plus 20, that's 32, multiplied by our time, right? Yeah, which we need to find. And this is multiplied by 2 because there are 2 workers. And I made a small slip. The fact that I didn't change the numbers much. Yeah, I did say that a while ago, but no, numbers weren't changed much. God, I feel like talking about bird brains and all really might have frazzled my brain a bit. Anyways, now what we have here is well, since the numbers haven't changed much, this side's going to be 1 by 30. This side's going to be 1 by 30, and this side's going to be, the only difference is now there's an additional factor of 2 here, so it's going to be 1 by 80. You might have guessed the answer is 30 by 8, or double of what it was before, which is 30 by 8 is what? 30 by 8 is, let's see, that's 15 by 4, that's 3.75. It's going to be in days. The unit's going to be days because it was for the left hand side all along. Okay, so that's 3.75 days. um, we uh, we were it was a good thing that we didn't attempt this sort of logic, keeping worker 2 waiting for the rest of the time. So that would be incorrect. Now just one last problem, and this is where this formula, I feel like this is where it shines the most out of all of these problems. Now we have three working units, you could say, okay, and really I could guarantee if you do this using your work rate formula. I don't know whether for this particular problem there are some simplifications. Maybe it wouldn't take a while that long, but in general it really would take a while if you just attempt it using your um, good old work rate formula. What we're going to do is, okay, so let's first write down our the values of our variables. So company A can fix all the electrical connections in a food production factory in 15 days. So that's our T1. And actually this is I should check this, that is combined work. Well, I set the problem that way. It is okay. All three companies, they're jointly contracted. Anyways, we're getting to that. And all the electrical connections in a company, so in one food company. So that's going to be our W1. We don't need to care about something like there are X connections in one food food factory. Just this much is enough, really, considering W1 to be one factory. Companies B and C can do the same job in 2/3 and 4/5 of the time. Now this is interesting. This gives us some info about the time and the rate also. Okay, we'll see that in a bit. Okay, we'll have to do some substitutions into the problem. We'll see that in a bit. Okay. If all three companies are jointly contracted by a multinational food brand and took 24 days to complete the work, the job, so 24 days, it's going to be my T. Okay, that's going to be my T, time in the combined situation. How many factories of the brand did the work on? Okay, so how many factories? So we basically need to find the work. Okay, so the combined work, really. So how many factories did the work on? All right, I'd encourage you to try it yourself by pausing the video. All right, so I'll assume that you have taken a shot at it, and now let's work through it. First, I'll write down all that we know here. So again, it's really the same as what we have been doing before. Instead, here only difference is here there are three working units. Okay, three companies. So it's going to be three terms here on the left hand side and multiplied by 3 instead of 2, okay, on the right hand side. So keeping those in mind, we have W1, which is 1, divided by R1 into T1. Now I'm going to keep it like this for a bit, and you'll see why. Okay. Plus W. Okay, so do the same job, right? Do the same job here is what they said. I just missed that. So basically it's the same thing as saying companies B and C also work working on one factory individually. So W2 and W3 are also going to be 1, okay. So what we have is 1 by R2 T2 plus 1 by R3 T3 equals W, okay, that's what we need to find, divided by R, the rate, the combined work situation, multiplied by the time taken. So just 24 days. Okay, and this has to be multiplied by 3. Really need to be careful here. This factor is quintessential. So now about the substitutions I was talking about, notice this for these individual situations, okay, like for company 1, company 2, company 3, sorry, ABC, um, they did the same amount of work, right? They did the same amount of work, okay. So um, it makes sense to say that if we go back to our original work rate formula, that the product of rate and time is going to be the same, right? It's the same work, the same amount of work, okay, one unit, one factory. So the product of rate and time for each of these, okay, is going to be the same. So let's write that down. R1 into T1 equals R2 into T2, that equals R3 into T3, R3 into T3. All right, so interesting. Now we can just substitute this, these two, the fact that R2 T2, okay, is the same as R1 T1, and this is also the same as this, okay. We can substitute this, okay. So we can put this, okay, R1 T1 instead of R2 T2 here. You can put it here too, and and yes, we also know that T1 is actually 15, okay. T1 is actually 15, okay. T1 is actually 15. So this whole left hand side turns out to be 1 by R1 okay. So yeah, R1 into T1, and T1 is 15, and we basically have this a total of 3 times here, right? R2 T2, same thing as R1 T1, R3 T3, okay, same thing as R1 T1. So we have this 1 by R1 into 15, a total of 3 times, so multiplied by 3 on the left hand side, and this is going to equal W oops, different color, W divided by R. Now wait, didn't find that yet. Yeah, okay. So so we have our R2 and R3, which we need to express if we want R, because it should be pretty apparent. Our combined rate is the sum, right? It's the sum of 3 rates, R2 plus R3. All right, so and how do we find that? Well, what we have here, okay, so if I drag this out here, if I try to express R2 in terms of R1, I'd get R2 equals R1 multiplied by T1 divided by T2, right? Okay, so and here it's been said that company B, okay, did the job in 2/3 of the time, okay, in 2/3 of the time. Well, that means T2, that basically means T2 divided by T1 is 2/3, right? That's 2/3. Okay, so then what's T1 divided by T2? Well, that's just the reciprocal of this, right? So that's 3 by 2. So that's 3 by 2, or 1.5 R1. Okay, same process for R3. R3 is gonna be R1 multiplied by, well, the reciprocal of the factor here basically. So it's 4/5 here, so we're going to take 5 by 4, okay, 5 by 4, so 5 by 4. or 1.25. Okay, so R3 is 1.25 R1, and the sum here is going to be, so 1 plus 1.5 plus 1.25 multiplied by R1. Okay, this is 3.75, yeah, 3.75 R1, 3.75 R1. All right, and I think you can already see the purpose of why I'm trying to express everything in terms of R1, okay, or everything related to rate, is now I have R1 on both sides, which I can cancel. Okay, so R here is actually 3.75 R1, right? That's multiplied by 24, and this thing on the right hand side, there is a factor of 3 also. All right, so we have our equation. Okay, I'll partition that away from this. Okay, so we have our equation here, and interestingly we can cancel out R1 as intended. To cancel out 3 here also, 3 can also be cancelled out. That's pretty neat. So W is just, we rearrange this, we get W equals 3.75 multiplied by 24 divided by 15. Okay, that gives us so 3.75 multiplied by 24 divided by 15, that's 6. Okay, so and well, all the work it was the unit for work was factories. So how many factories are we working on? This is 6 factories. Okay, 6 factories. So basically the answer that we have arrived at is the 3 companies in their work contract, okay, the time for the in the duration of their contract, they worked on 6 factories, okay, of this multinational food brand. Fascinating. So just to recap, just to put an ending note here, work rate problems can often be done pretty quickly just using our basic work rate formula. Sometimes they can get a bit hairy, especially the number of things that are different in the both sides, or different situations. Okay, the number of variables that have different values, you could say. So the more of them there are, the more confusing the problem becomes. And so surefire method that always works, okay, if you have 2 instances, okay, 2 different instances of the same activity, we can use this formula. Okay, so W1 divided by R1 T1 equals W2 divided by R2 T2. To find any one of the variables, if we know the rest, or if we can express them as some multiples of each other. Okay, so and need to be aware that all the quantities on both sides need to have the same units. Okay, and with that we also encounter problems commonly known as combined work problems. Okay, so basically the efforts of several units, okay, several working units, could be people, could be machines, could be anything, are being added together. Okay, they're working together, and for that situation basically it's this expression, okay, this cornerstone expression of ours, which we have been which we saw, which is a part of the previous formula too. So basically this expression added for each of the units will be equal to the same expression for the combined work situation multiplied by the number of working units, and we saw how that formula was derived. Okay, and it again the units need to be the same for each quantity on both sides. And with that, that's the end of this lecture. I hope you've found it helpful. I'm really new to this, so I'm pretty sure that there's a lot to be dissatisfied about. I'm free to suggestion. Okay, I'm free to any criticism, suggestion, what was that called? Yeah, constructive criticism. So I'm free to any of that. Please do make any suggestions that you want. If you want me to cover some topic, please do write that in the comment section. Um, I do have my own plans, but depending on the suggestions, and if I seem to like one a lot, I might do a video on that soon. Also, if you found this video helpful, please do support this channel, leave a like, subscribe, and turn on the bell to get any notifications or when I post a new video. And with that, that's the end of this lecture. Hope you found it useful, and study smart.